Okay, so Newton's third law works like this, guys. Forces act in pairs. If you exert a force on something, it will exert an equal and opposite reactive force back on you. Okay? It is often stated like this. Every action has an equal and opposite reaction. Okay? That is Newton's third law. It is most often misapplied to sociological situations. Okay? People say stupid crap, get smacked in the face, and then say something like, oh, every action has an opposite reaction. No! You said something awful and we're smacked for it. That's not physics. Okay? That's not where that thing applies. Okay? This applies to situations like right now, me standing right here. Okay? Gravity pulls me down into the floor, and the floor pushes back with an equal and opposite reactive force. And thus, I don't move vertically. Okay, I just stand there. Okay, the same thing is going on for you in your chair right now. Gravity is pulling you down into your seat. Your seat is pushing back with an equal and opposite force, and then thankfully you don't either fall through the floor, okay, or fly off of the seat. Okay, because those forces are always equal and opposite. Okay, it is also why if you were to hit somebody, you could break your hand. Okay, if you punch somebody in the face, not that anyone would do that. Okay, but if you did, okay. When you exert that force on their face, okay, their face exerts an equal and opposite reactive force on your hand. Here's the problem with that. Their head has more mass than your hand. So the acceleration your hand experiences is greater than the acceleration their head experiences. And as a result, you can break the bones in your hand.
So it's just like how in a car crash, a smaller one is used.
Yeah, that's exactly right. Mass matters, right? Okay, and so the smaller mass is going to experience a greater acceleration. Okay, another example, if I push on the wall, so if I'm standing right here, okay, and I'm facing the wall, and I push on the wall, what's going to happen? Yeah, I'm going to move backwards. What's the wall going to do? It's going to go that way. Listen, you'll be able to hear it move. Okay? Now, obviously, it doesn't move nearly as much as me. It's far more massive and anchored. Okay? But it still had some change in shape. Okay? The whiteboard flexed a little bit. You could hear the flex in the whiteboard. Okay? It's not because I'm huge. Okay? Just because the whiteboard flexes a little bit. Okay? But I moved quite a bit. I pushed right off of the wall. That's an opposite reaction. I pushed on the wall with, I don't know, probably 200 newtons worth of force, and the wall pushed back on me with 200 newtons worth of force. Okay? This is why I was telling you when we watched that video of the guy who floated off into space because he ran out of propellant. Okay? Why you should always take a wrench with you if you're doing an EVA. Okay? If you're an astronaut and you're leaving the spacecraft, you should always take a big, heavy tool of some kind with you. That way, if you were to become stranded, you could do what with the wrench? Yeah, push it away from you. Okay? If you push on the wrench will push back on you with an equal and opposite reactive force. Okay? So if you had your back to your spacecraft, you could push the wrench, and the wrench would push you in the direction of the spacecraft. Now, how long does that force last for?
It's compression.
No, actually, it only lasts for the instant that you are pushing on the wrench. Okay? Once you've let go of the wrench, it's not exerting a force on you anymore. You're no longer accelerating, but are you moving? Yeah, now you've achieved some small amount of velocity in the direction you wanted to go. Okay? And in space, that velocity is perpetual. Okay? There's nothing to slow you down now that you've gotten moving except hopefully running into your spacecraft. Okay? Does that sort of make sense to everybody? Okay? That's how all of those propellant things worked on all the spacesuits that we saw. It's how in The Martian, Mark Watney went Iron Man. Okay? He allowed the escaping air in his glove to act as a thruster because there was pressure inside of his suit. The gas pushed on the inside of his suit. The suit pushed on the gas and forced the gas out, okay? Which exerted a force on him in the opposite direction. That's how all thruster systems work, okay? Including if you blow up a balloon, okay, and you let it go, right? It kind of flies everywhere, right? That's what happened to Mark Watney. He was essentially just a balloon that was going all over, okay? So you have the inside of the balloon, okay? You have the air pushing on the inside, the balloon exerting a reactive force back. If you let it go, okay, that'll result in movement. Making sense? Okay. So Newton discovered that all forces act in pairs, okay? And that every action had an equal and opposite reaction, okay? He called the paired force the normal force because it kind of kept things normal. Without it, things would fly everywhere, okay? Or nowhere, or whatever. It would be really weird. So this was the normal force. It kept things normal, okay? Understand that for every action, there's an equal and opposite reaction. Those are 3 key points for today. Okay, so if you're in a football game, you're lined up like this, okay? You got the offensive and defensive lines right across from each other, okay? The ball is snapped and the two of you crash together, okay? You feel a force, but so does the other person, okay? You exert a force, they feel it, right? And that's because of that, again, you exert a force, they exert a force back. You both feel the effect of the collision, right? Whoever has the bigger mass is the one who will move or who will accelerate less, okay? Which is why linemen typically are the biggest people on the team, okay? They have the largest mass because having a bigger mass means they're going to be harder to move, okay? They're going to experience less acceleration due to any forces they experience, okay? Same with sumo wrestlers, okay? You never see a skinny sumo wrestler, okay? They would never make it because being a sumo wrestler is about pushing the other guy out of the ring. Okay, and the more massive you are, the harder you are to move. All right. Okay, imagine this situation here. For some reason, this person got in this canoe and forgot the paddles. They drifted slightly away from the dock. They don't want to swim for it, so they figure if they run down the canoe and jump, they can get to the dock. True? Not true?
Not true.
Everybody's shaking their head. Everyone should be shaking their head like this. Absolutely 100% possible. Here's what we envision though. The boat's on the water. Water's slippery. If I try and jump off the boat will slide out from underneath me. Yes, it will. But when you push on the boat, what's it going to do to you? It's going to push back. Okay? Does the boat have as much mass as you? No. Okay? But if you time this right and you jump the right way, you can get to the dock. If you don't do it right, you will lose your teeth on the dock, okay? And you'll get wet, and that was probably not what you want, okay? The key to this is if you just push backwards on the boat, like this, the boat will just push forwards with an equal amount of force. The problem is that your acceleration will be much less than the acceleration of the boat, okay? But you'll still get a push. It'll be harder though because you're not pushing on a lot of mass. If instead of pushing straight back, you push down and back, which way will the boat push? Right, okay, it'll push this way. Now, the advantage of that is you're not just pushing on the boat now. What else are you pushing on? All the water under it. Now will the boat move as much? It'll move down a little bit, the water will move a little bit, but you won't get as much of that sliding action backwards, okay? And so you'll get more of a push, and then you can follow a projectile arc like you learned in Unit 1 that would actually end up with you on the dock, okay? The problem, what's that?
You'd have to swim back to get the boat. Because if you jump through something.
Oh, yeah, you're right. Someone asked, but if he gets back on the dock, he can get another boat. And this time, remember the paddles and go after the boat down. Yeah. Okay. Yeah, you're right. I mean, if there's no other boats, either that boat is gone or he has to swim for it anyway. But maybe he's got a wetsuit. I don't know. It's a very hypothetical situation. Getting far too real here. Okay. But yeah, so that's how you could do that. You could actually accomplish this if you did it right. Okay. But you have to kind of harness Newton's third law and instead of letting it work against you. Okay. Which is what would happen if you pushed straight back. Okay, it would simply slide out. Okay, you're right. It would look, that's what everyone envisions. But if you do it right, okay, then you get more of an upward push and you can get there. Okay. So, let's look at this very simple Newton's third law example. Here's the thing with Newton's third law. There's no formulas. Newton's third law doesn't have any formulas. It's just Newton's second law. Okay, when it comes down to the math of it, all we're using is Newton's second law. So, I've got this situation. The astronaut has a mass of 90 kilograms. The spacecraft is 11,000 kilograms. Okay, and the astronaut exerts a force of 36 newtons on the spacecraft. Okay, so this force here is 36 newtons. So what's this force? 36 newtons, but it's negative. Okay, that's all I have to remember in order to be able to do this question. If the astronaut exerts 36 newtons worth of force, the spacecraft exerts negative 36 newtons worth of force. Equal and opposite every time. So now I can calculate the acceleration of the astronaut. Let's color these. Okay. All right, so the acceleration of the astronaut, okay, is going to be the force exerted on the astronaut divided by their mass. Okay, so that'll be negative 36 newtons divided by 92 kilograms. And so 36, sorry, negative 36 divided by 92. All right, so negative 36. So their acceleration is going to be negative 0.39 meters per second squared. Is that very fast? No, and it only lasts for as long as they're pushing. Once they lose contact with the spacecraft, they can't push anymore, the acceleration is done. They're not going to move very fast. The problem in space is they move forever if there's no other way to change their velocity. Okay, so you could float into oblivion at 0.25 meters per second. Okay, that would suck. Right? But for the spacecraft, same idea. Okay, now what's the spacecraft's acceleration going to be like comparatively? Bigger or smaller? Way smaller. Okay, look at the spacecraft's mass. It's only getting 36 newtons of force too. Okay? 36 newtons worth of force on 11,000 kilograms is not going to produce much acceleration. So that would be 32 millimeters per second squared. Okay, is that very much? No, the spacecraft hardly feels that. Okay, it's a little bit, but it's not much. And it's only for as long as the astronaut is pushing. All right, is that fairly straightforward? All right, so we've already gone over the reasoning. Skip that, we did that already. All right, so action-reaction is responsible for us being able to walk, okay? Very simple. If I want to walk forwards, which way do I push? Yeah, I actually push back, okay? I'm trying to push the floor that direction, okay? Because there's enough friction between my shoes and the floor, okay? My foot doesn't slip, and friction provides me a force forwards, okay? I'm simply relying on that. If I'm pushing straight backwards, okay? Watch people walk. Some people push more backwards than others. Some people push more upwards. That's what makes some people walk and their head kind of stays along the same level. Okay? Those are people who push almost straight backwards, and some people kind of walk like this. It goes up and down. They push a little bit more down to get a little more force off the floor. Okay? It's weird, but it's true. You'll never watch people walk the same again. Okay. What if I want to jump? I'm not going to jump because I'm old and now have a credit card vertical. Okay, I'm not going to embarrass myself by jumping up here. Okay, but if I want to jump, what do? Besides bend my knees, swing my arms, and go for it. Push straight up. I push straight down. Yeah. When you jump, you're actually being thrown off the floor by the floor. And we all think it's because we have strong legs and we can just push and we push ourselves off the floor, but we don't. We just push the floor down as hard as we can. The floor doesn't move, okay? So it exerts an equal and opposite force in the opposite direction. If that force is greater than gravity, you fly off the floor. Okay, that's how jumping works. Okay, the harder you push on the floor, the harder the floor pushes back, the higher you jump. Okay, weird, but true. All right, now, here's the thing that goes wrong with this, okay? People get this idea, they see, okay, I exert a force on the floor, which is really the earth, and the earth pushes me forward, and I move forward. So if I move forward, the earth moves backward. And then they get this idea like Nike got, which infuriates me every time I see the damn ad. Luckily, they don't show it anymore because they had Kobe Bryant in it, so they don't show it for that reason anymore. But, okay, they get this idea that the Earth is stopped spinning, and they need to get it spinning again. So they get everybody in the world to run the same way to get the Earth spinning again. It is the dumbest thing ever, okay? Because they get this idea that even if everyone ran the same way, they could actually cause some change in the Earth's rotation as a result, okay? First off, it's way more complex than that. The Earth is not a completely solid ball, okay, where that would work. There's the mantle and the molten core and all that kind of stuff, okay? But also, there's the Earth's mass, okay? The Earth has a mass of 5.98 times 10 to the 24 kilograms, okay? If everybody on Earth had a mass of, let's say, 60 kilograms. That's 7 million, right? Okay. That would be the mass of the Earth's population. It isn't anywhere close to the Earth's mass. Okay? The effect that we could possibly have on the Earth's rotation as a result of us doing anything is ridiculous. Okay? There's also this idea that if everybody jumped at the same time, we could bump the Earth out of its orbit. Okay? It's just stupid. Okay? The Earth is not, again, like that. All right? We could never impart enough force to do anything to the Earth's rotation. Never mind getting everybody into one place at the same time in order to get everybody to jump and synchronize that jump across 7 billion people. Okay, it just wouldn't work. All right. Now that that myth has been busted, if you ever see that ad, you can be as infuriated as me every time you see it. I'll try and find it if we have time. All right. Real world application, Newton's third law. Okay, you've probably seen that, the crazy people who take those little U-Haul trailers and they tow them behind completely inadequate vehicles and they drive 120 with them grossly overloaded down the Deerfoot, okay? And they're just a menace to everybody, okay? Most of those vehicles that are towing those trailers do not have hookups for electronically actuated braking systems, okay? So what U-Haul has built into their trailers is a reaction braking system. There's a spring-loaded tongue that goes onto the ball, right? So when you slip the ball over top, you slip the hitch over top of the ball, okay? If you stop, what does the trailer want to do? Right, Newton's first law, so it's going to keep going. But you're here, so it's going to hit your hitch ball, okay? Now, when it hits the hitch ball, there's a spring-loaded mechanism here. So as it starts to push on the ball pushes back, and that compresses the spring that actually applies the brakes on the trailer. It works fine as long as you're not going way too fast, like most people do, even though there's like a half a dozen signs all over the thing that says maximum 80 kilometers an hour, okay? And if you don't have to slam on the brakes suddenly. Because if you slam on the brakes suddenly, all this trailer does is rotate, okay? Something called jackknifing, all right? Semi-trailers do it all the time, okay? So if you're slowing down reasonably or slowly, okay, then that mechanism, that Newton's third law reaction mechanism, will actually apply the brakes on the trailer and make them stop safely. Okay? Otherwise, all you get is a trailer that's really pushing on the back of the car and then usually tries to rotate around it. Okay? All right, making sense. All right, so we're going to look at a few examples here. So this is a Newton's third law example. It looks like some of the ones we've done though, because it's multiple masses. Okay? So we got these 3 boxes, and they're positioned next to each other on a horizontal frictionless surface, so there's no friction. Okay? An applied force on box A causes all of the boxes to accelerate at 1.5 meters per second squared to the right. We want to calculate the force exerted by box C on box B. This is a she ate the spider to catch the fly kind of a question. This force causes this force, so this force has to go because of this force, and so on and so on. Okay? It can get a bit convoluted. So we want to find the force that box C exerts on box B. So what I'm going to do is I'm actually going to break this thing down so that I'm just looking at boxes individually. I already know that each one of those boxes has this acceleration. Can I calculate the net force on each box with that number? Okay. So I'm looking for the force that box C exerts on box B. Do I need box A at all for this? I'm talking about C and B, so I don't even need box A. All right, so if I'm looking at box B, that's the 10 kilogram one. Okay, the forces that are acting on box B are the force of A on B and the force of, nope, there's no friction. What's the force I'm being asked to find? Right, the force of C pushing back on B. So that's the force I'm being asked to find. I can calculate the net force. That's easy enough. Mass times acceleration. Okay, so that'll be 10 times 1.5. So the net force is 15 newtons forward. Okay, that's great. I have a big problem. I have a force I'm supposed to find, and two of them are unknown. Does that leave me with a problem? It's a huge problem. The problem is I cannot solve this problem with box B. But I can solve it with box C. There's no friction in this question. What's the only force acting on box C? Being pushed forward by box B. Okay. What's the relationship between this force and this force? According to Newton's third law. They're opposites, and they're equal. Okay? When box B pushes on box C pushes back with an equal and opposite force. I can't calculate that force using this box because I don't have enough information to do it. But this force, which is equal to that one, is the only force acting on that box. And I know the acceleration of this box. Since this is the only force acting on this box, it is also the net force acting on this box. Would you agree? And I can calculate net force by going mass times acceleration. 5 times 1.5, 7.5 newtons. So the force that B exerts on C is 7.5 newtons forward. So what's the force that C exerts back on B? 7.5 newtons backwards. How convoluted is that? Pretty convoluted, right? We had to do a lot of diagramming and a lot of thinking in order to get to a very simple mathematical operation. Okay? But as long as I remember that forces act in pairs, I can do it. I just kind of have to get to that point through my reasoning. How many people are looking at that and still going, yeah, okay. So here's what we have to remember. The question wanted to know, how much does C push back on B? The only reason that C pushes back on B is because B pushes on C. those two forces are equal than opposite. They're an action-reaction pair. So as long as I can find one of them, I know the other. And that's the whole reasoning that I went on when I started this question. Okay? I needed to find this force, but I couldn't use this box to find it. So I used the action-reaction pair of that force on a box that I could find it on. Okay? As long as I remember forces act in pairs, I can use that kind of reasoning to calculate them. Okay? Let's try a different one. Okay, so now, same situation, same boxes, but now I want to find the force that B exerts on box A. Okay, so here's box A. Did they tell us what force was applied to that? No, they didn't. Okay. Okay, so these are the two boxes that are involved in what they're asking me to do. They want me to calculate the force that B exerts on A. Now, is that part of an action-reaction pair? The force that B exerts on A is equal to what other force that I have diagrammed on here? Right, this one. Those two are an action-reaction pair. They are equal but opposite. Okay? Now, if I look at box A, I can calculate the net force on box A, but that's it. I can't calculate anything else. The question never tells me what the applied force is, so there's no way for me to calculate this force that they want with this box. But with this box, I've already calculated this force. Okay, we did it in the last question. It's 7.5 newtons. Okay, I calculated it already. The net force on this box is mass times acceleration. Okay. What's the other way to calculate net force? Right, the sum of all forces. Yeah, that thing, right. Okay, so F net for box B, okay, is going to be the force of A on B plus the force of C on B. Okay, those are the two forces that are acting on it. Okay, that's going to mean that 15 newtons, positive 15 newtons, equals negative 7.5 newtons plus the force of A on B. So can I calculate how hard A pushes on B? I can. Okay, I'm just going to subtract the 7.5, negative 7.5 over here. Right, which is going to give me negative 22.5, sorry, not negative 20, positive 22.5. Okay. So for there to be a net force of 15 newtons forwards on box B, there has to be a 22.5 Newton force forwards and a 7.5 Newton force backwards. Are you all right with that? Okay, so now I know how hard A pushed on B. Positive 22.5 newtons. How hard did B push on A? Okay, remember, at the start of this question, we said this force is in an action-reaction pair with this force. One of them causes the other. So they are equal but opposite. So if this force is 22.5 forward, this one is 22.5 backwards. Okay, so as long as I know where my action-reaction pairs are, if I can find it using either part of the pair, I know what the other one is. Okay, and that's what I've done here. There was no way for me to calculate the force they wanted with the first box. So I found its action-reaction pair using the second box. Okay, it was still part of that one, and I had enough information with that box to do it. All right, everybody okay with that idea? Okay, this one's only got 2 boxes. So it's less convoluted because there's only 2 boxes. Okay, they're placed next to each other on a horizontal rough surface. So now there is friction. Okay, an applied force acting on box A causes both boxes to accelerate at 2.6 meters per second squared to the right. The magnitude of the force of friction on box B is 28.3 newtons. Calculate the force exerted by box B on box A. Okay, so you know they both accelerate at this rate, which means you can calculate the net force for either box. I would suggest you draw a free body diagram for both boxes and see which box you need to calculate the force that B exerts back on A. I'll give you a few minutes on that. Okay, have we decided which box is best to use to answer this? B. I don't have enough information to use box A. I don't know the force of friction on box A. I don't even know the applied force acting on box A. I know nothing other than the acceleration of box A. So box A is useless to me here. Okay, what I want to use is box B. So I'm going to draw a free body diagram of box B. Do you notice how even though these are Newton's third law questions, they become Newton's second law questions? I mean, all we're doing here is sum of all forces in M times A, right? So I said there's no separate formula for Newton's third law. It just comes back to Newton's second law. Okay, so we got an 8.5 kilogram box. It is being pushed this way by the force of A on B, which is a reaction pair with that force. Is everybody okay with that? The force that A exerts on B is equal but opposite to the force that B exerts back on A. So if I can find that force, I have my answer. Agreed? Okay. The other force that's acting on box B is the force of friction, which they told us is 28.3 newtons. All right. I know the acceleration of box B, so I can calculate the net force. 8.5 kilograms times 2.6 meters per second squared. Okay, so 22.1 newtons is my net force. Okay, 22.1 newtons forwards. So we'll say that's positive and we'll make this one negative. All right, so that F net then equals the force of A on B plus the force of friction. I know the force of friction and I know the net force, so now I can calculate the force of A on B. I'm going to subtract the force of friction over to the other side. So I'm going to have F net minus FF equals F of A on B. All right, so that'll be 22.1 newtons minus negative 28.3 newtons. Okay. All right, so we're looking at 50 newtons forwards for the force of A on B. So the force of B on A would be 50 newtons backwards. Okay, everybody all right with that idea? I think there's only 2 significant digits there. Yeah, all the masses have 2. Okay. So again, it's still Newton's second law. It's just even more convoluted reasoning than what we were doing before. Okay. All right. Anybody ever shot a gun before? Okay. When you fire the gun, what do you feel? You feel the recoil. What causes recoil?
The force of the bullet goes out, acts backwards.
Exactly. It's Newton's third law. Okay? When you detonate the powder that's in the round of a bullet, okay, the gases expand within the chamber, okay, and down the barrel of the rifle or pistol or whatever it is you're firing. Okay? So as those expanding gases push on the bullet pushes back with an equal and opposite force. Now, because you and the rifle are much heavier than the bullet, that recoil, that acceleration is much smaller than the acceleration the bullet feels because of its incredibly small mass, but it's still there. Okay? If you've ever fired anything, like especially like a shotgun or something like that, okay, you need to make sure that they are properly braced against your shoulder. Okay? If they're not, they're going to rotate very quickly. Okay? People who, like in movies, shoot guns, like it's just completely unrealistic. Okay? How they do that and how they don't get a gun in the face. Okay? As a result of it. Okay? You see people holding like high-powered rifles out away from their body. Okay? All that's going to happen is the gun will fire and move backwards, hit their body, and then rotate up into their face. Okay? It's the same if you're holding a pistol and you don't know how to brace yourself. Okay? You just hold the pistol up in front of you like this and you pull the trigger. You're going to get it right in the face. Okay? You ever watch someone who knows what they're doing? Okay? They hold it to the side and they brace themselves and they brace this arm so that when the kick happens, they're ready for it. Okay? It kicks back into them as opposed to up. Okay? They brace themselves for that type of force that's going to come. If they don't, this will happen. When we were doing Newton's second law, I gave you a question that was very much like this one. You guys had no problem with it. Okay, so I want to see if you guys can do this one now. So you have two logs attached by a chain. Okay, one log is being pulled, okay, directly by a team of horses, and the other log is attached to the first log. Okay, so you've got logs A and B. Okay, a light chain connects log A with a mass of 150 kilograms to the horse's harness. Log B, that has a mass of 250 kilograms, is connected to log A by another light chain. Okay? The horses can pull with a combined force of 2,600 newtons, and the ground exerts a force of friction of 2,400 newtons on the log system. Okay? Calculate the acceleration of the logs, and then for part B, they tell you the force of friction on log A is 900 newtons. Okay? Calculate the force exerted by log B on log A. All right, I'm going to give you guys a few minutes to try that one. Okay? The answers are there. So you can check and see if you get them right as you go.